and then it should start. Cool, I see a couple people joining. So hello, everyone. Oh wow, a couple people joined right now. Perfect, so that's good timing. So yeah, I just started recording. So just so everyone knows, it'll be posted to YouTube likely by the end of tonight, along with any lecture slides and stuff like that. And yeah, I'll pass it off to Elon. I think they're going first. So yeah.
So hi everyone, thank you for coming to the workshop. Today we're just going to do a brief introduction to neural networks. We're not going to get into too much math or anything, just an overall general idea of what they are, how we train them, and what can we do with them. So let me share my screen. Okay. Can everyone see my screen? Or
Yep, we can see your screen. We're all
okay,
set.
cool. Okay, awesome. So before we dive deeper into what neural networks are, let's just look at where it fits within AI. Since we are the Carleton AI Society, where does it fit into the overall picture? So let's start off by what is AI? Well, AI is just techniques that enable computers, robots, and programs to mimic some sort of human intelligence. While machine learning is a subset of AI, which contains various statistical methods that enable for programs to learn without being explicitly programmed for learning those specific items. So machine learning is AI, but not all of AI is machine learning. So machine learning is a subset of AI. And within machine learning, there's deep learning, which deep learning is a subset of machine learning where we use artificial neural networks that adapt and learn from existing data. And this can include different tasks such as image classification, language translation, and many other endless possible tasks. And neural networks are really good for learning different types of patterns. But we never explicitly tell the neural networks what to learn or what pattern to look for. For example, if we're trying to classify based on an image of or we have two images, an airplane and a car, and we're trying to classify if one's an airplane or a car. We don't tell the neural network to look for wings or wheels. A good neural network will learn those patterns on its own. So now that we know a little bit of neural network or how neural networks fit into AI, let's dive a bit deeper into it. So let's start off by what are neurons? So neurons, or sometimes we refer to them as nodes, we can think of a neuron as holding a number. And it gets a various input signals, and based on those inputs and information contained within that neuron, it'll provide a value as the output signal. And what does it consist of? At least in artificial neural network. So we're not talking about within like biology in the brain. We're just talking about artificial neural networks. So the neuron consists of different weights, a bias, and activation function. And it uses all this within a mathematical formula, and it outputs the total or the neuron's activation. And it does this using an activation function, which we'll discuss later in this presentation. But the activation function contributes to which extent is the neuron activated. And it is a mathematical function that decides how important the current input is for the future layers of or for future neurons in the neural network. So now let's take a look at how some neural networks look like. So there are many different types of architectures, shapes, and sizes for neural networks. For example, there's one architecture called convolutional neural networks that deal with image prediction. There's also recurrent neural networks for dealing with text and speech data. We won't be covering this in this workshop, but highly recommend learning more about them through books, lectures on YouTube, and we also have a workshop that coming up that will discuss convolutional neural networks, so definitely attend that if interested. And the neural network pictured here is what we call a fully connected neural network. As you can see, it is composed of 4 layers that we'll talk about in more detail shortly. The fully connected neural network means that each neuron in the previous layer is part of the input to each neuron in the following layer. This is common, but not required when designing your neural network. So the input layer. And the input layer consists of the data that we have that we want to use to make the prediction. So we'll start by looking at this layer. And it's going to contain all the useful information that we can use to make the prediction. And this can be any type of information pertaining to, for example, financial data, images, text data. So it's all the input data that we have. So for example, if we're trying to classify based on handwritten digits, what number is in this image? We're going to use the properties of the image as the input layer. So for example, if we have a 28 by 28 pixel image, how are we going to input this into the neural network? Well, since the image is 28 by 28, I think it's going to be, let me just calculate it. So it's 28 times 28. It's 784 pixels that we have that make up the image. Well, each pixel is going to be an input neuron. So for example, we have the values of the pixel. So for example, if it's a grayscale image, each pixel is going to be from 0 to 255. And each one of those values, it's going to be the value of the input neuron. So if it's 28 by 28 pictures, we'll have 784 of these input neurons, and each value will, and each pixel value will be the input to the neural network. So moving on to the output layer, we'll skip the hidden layers for now and come back to it in a bit. But the output layer is to make a prediction. We want to look at the activation value of the final layer. And the value that we're going to predict as the output of the neural network is going to be the value in the output layer with the highest activation value. So for example, if this is the values of the active or the final layer, we have 0 0.1, 0 0.1, 0 0.6, 0 0.05, 0 0.1, 0 0.05. We're going to select 0 0.6 because it has the highest activation value for the output layer. And here you can see that all values add up to 1. And sometimes we want to model the output layer as probability. So we want to look at which neuron is the highest probability and to be the output class, and we want to select that value. But there's also some cases where we're not going to select one neuron. So there are some problems in different neural networks, or that we can use the neural networks to solve, that we might want to select more than one output neuron. So in this wouldn't be just single classification. This would be what is called multi-label classification. So can anyone think of problems where we might not want to classify one thing, but maybe multiple things? So I don't know if you can unmute your mic or type it in the chat, but if anyone has ideas where one might want to classify multiple things, feel free to mention. So based on an image, yeah. So for example, if a dog is mixed and we want to classify multiple breeds at once based on the image, for sure, that's definitely one. And yeah, all these are great examples. So ice cream toppings, there could be multiple in the same picture, different parts of a speech. Yeah, the one I had in mind is, given a movie poster, try to classify the genres of that movie. So for example, a movie can be both comedy, romance. It's a combination of different genres. But yeah, great examples. Yeah, and another question I have is, how many output neurons for digit prediction? So if you have an image of a handwritten digit, how many output neurons would we need? Yeah, 10, because we'd have to have one output neuron for each digit. And if we have cat versus dog, so if we're trying to classify an image based on cat, if it's a cat or a dog, we'd have to have 2 output neurons. So the input neurons and the output neurons, they're fixed based on our problem. So if we're trying to classify images of a fixed size and fixed number of categories that we're trying to output, that is always going to be fixed to the problem that we're working with. What is not going to be fixed is the hidden layers. And the hidden layers provide abstraction and break the problem into subcomponents. And this, as people programming these neural networks, that's what we have to change. And we have to think about when designing these neural networks. Thinking about just to give you a bit of intuition about what the neural networks do is think about an image of a handwritten number. Some digits have loops while others only have lines. So some of the hidden layers might be able to detect the subcomponents. So some hidden layers might, or some neurons might have higher activations if they see a line, or some neurons might have higher activations when they see a loop. And I have a small little demo that I found online. So are you still able to see my screen of this website with cars, or is it still on the presentation? Just want to make sure. Okay, cool. So this is a different type of neural network. So this isn't a fully connected neural network. This is a convolutional neural network. But I just kind of want to give you some intuition about how the hidden layers work. So for example, for convolutional neural networks, they use what we call filters in their hidden layers. And so, for example, for predicting cat versus dog image, some filters might be used specifically to detect the dog's paw, while others are used to detect tail. But we don't know that for sure because we don't tell the neural network exactly what to look for. The neural network learns that on its own. So here we have different patches, and think of each one for, I guess, each one is a filter. So some filters might have higher activations for different parts. So for example, so look at the first row. So they're all taking the input of a car, but different parts of the image light up more than others. So for example, this one right here, can you see my mouse? It lights up more for the trunk. So maybe this filter specifically looks for different trunks of a car. Well, so I guess if we refresh this page, you'll see different things that light up more. So yeah, so here's they're trying to predict the dog. And as you can see, these filters light up differently based on the input image. And that's kind of what I want to try to convey with the hidden layers, is that they look for these subcomponents of the image and they try to learn an abstraction of it. So going back to the presentation, and the number of hidden layers and the number of neurons in each layer, that determines the capacity of the model. And just kind of to reiterate, is do we know exactly how neural networks will break down the problem into these subcomponents? No. That's because we don't tell the neural network exactly how we should classify different objects. It should learn that on its own. And ultimately, the neural network should learn how activations in one layer help calculate the activations in the next. So back to the capacity. I have a small demo about this, but just before we go to the demo, the capacity is determined by both the number of nodes and the number of layers in the model. So going to the demo. So this is another website. So I forgot to reference the first website is by a course at Stanford called Convolutional Neural Networks for Visual Recognition. They have this little demo, which is neat. And this is also part of a demo showed in the course. So here's a network that they just have in the browser. and we can change different parameters and see how it reacts. So let's choose spiral data and see if it can learn how to separate the green from the red. So here we have, it's a 2-layer network, and we see that the first layer has 6 and then the second layer has 2. So what happens if we change the first layer to only have, let's say, 2 hidden neurons? Not hidden neurons, just 2 nodes and 2 neurons in the hidden layer. So we see if it only has 2, it doesn't have the capacity needed to separate between the green and the red. It doesn't have enough nodes to do that. But let's say if we increase it to 10, or let's do 5 actually. With 5, it's able to learn pretty well, but still, as you see, that the decision boundaries aren't perfect. So you see how it might still miss some red at the edge right here. What if we change, instead of 5, let's do 15. So with 15, you see it gets better. It has the capacity needed to model the decision boundaries and classify most of the data correctly. And let's just do random data. Here you see that it's able to classify different things. Some are correct, some are not. It's not clear. And what if we increase 15 to, let's say, 150? So going way, way over. What happens, it gets better. It's able to classify more correctly. But one thing to note is that if we increase the number of neurons too big, then what's going to happen is it's going to overfit, and it's going to make these decision boundaries that might work well for the training data, but it's not going to generalize well to unseen data. So the number of nodes in the hidden layer and the number of hidden layers, it's something that we have to experiment with and figure out what's the right amount for our problem. Because even you saw like the spiral data and the random data, the number of hidden neurons to separate the green and red dots varied for both. We didn't need as much for the spiral data, but we needed much more hidden neurons for the random data. But I think we kind of went overboard with 150, but I think like a lot less would work too. So like if we do 30, yeah, see with 30, it doesn't generalize as well because see it misses some, or I guess I didn't wait for it to finish training. But yeah. Yes, with 30, it still performs pretty well. So 150 was definitely way too much. And yeah, if you have too much, it could lead to overfitting. So now we move on to the forward pass, and this is how we make predictions. It is the process of taking the input values and traversing through the neural network and calculating the activations in each layer to input to the next layer until we get to the final output layer. And that's where we can make the prediction. So back to the building block. How do we calculate the activation value? Well, first thing we do is we get the activation values from the previous nodes, and then we take the associated weights for those. And we also have a bias term, and we just calculate this product and add it to the bias term. And then we take the input activation and pass it to an activation function, which we'll talk about shortly. And with this activation function, we get the value that we will output and pass to the next layer. Or it'll be the value that we predict for that output node. So the activation function, you've heard me mention activation function a couple times already. So the activation function decides to which extent should the neuron be activated. It is a mathematical function that decides how important the current input is for the next layer. It is important for the activation function to be nonlinear to be able to solve non-trivial problems while not using large amounts of nodes. Otherwise, if we were to use linear functions or not use any activation functions at all, the neural network will be a linear function itself. And by using nonlinear activation functions, it allows us to have some complex mappings within the neural network, which ultimately help solve challenging problems. So here's a couple examples of activation functions. If you attended some of our previous workshops on linear classification and regression, linear classification, then you have seen the sigmoid function. And the sigmoid function is nice because it takes an input and it maps it within the range of 0 and 1. And here in the middle, you see the linear function, and that's kind of what we don't want to use for neural networks, because the linear function, we want to use something nonlinear. And something that's very popular nowadays is the ReLU function, which basically you pass the input, and if it's less than 0, then it will return 0. But if it's greater than 0, it will just return the value itself. So that's probably the most popular one I've seen that's used a lot. There's also the leaky ReLU, which you pass in a value. If it's less than 0, then it will just multiply the value by 0.1. Otherwise, it will pass the value itself. So these are just different activation functions, and people experiment with them and see what works best for their neural network. So moving on to the last part of the presentation, and that's how we train the network. So what does it mean for the network to learn or train? That means finding the best weights and bias values for the neurons that will optimize solving the task at hand. The weights are the only thing that's going to be modified within training cycles, or we call them epochs. But we do this by using backpropagation, which is a set of algorithms that help the network learn. It works by computing gradient and the loss function value as a result of the current weights and prediction output. Algorithms such as gradient descent mentioned in our previous workshops are used here as well to minimize the loss values. It does work slightly different, unlike linear classification, because we have multiple layers. So to accomplish backpropagation with each layer, we need to use the chain rule to multiply the node's local gradient with the global gradient. Local gradient multiplied by the global gradient. And I won't go into much more detail on that, since the purpose of this workshop is not to be too math heavy and just give a brief introduction. Although I believe it is important to know the math behind how it works, most neural network libraries available and people use, such as PyTorch and TensorFlow, handle most of the math for you. And as you can see on the image, as you're training the network and performing backpropagation, you want the loss value to increase. And as the loss value increases, you want the accuracy to increase. But if you overtrain and the loss value gets too small for the training data set, then the test set might start having worse performance. So it's important to train it just the right amount where you don't overtrain it. And the last thing we'll talk about is optimizers. So when performing gradient descent or other algorithms that minimize some loss function, we want to take small steps until we find some minimum for the loss function. And different optimizers have been introduced to improve the convergence of backpropagation. And the optimizers define how the weights should be updated so we can hopefully converge to the optimal weights faster. And just you see this image, these are different ways we can update the weights. And you see some of them are able to converge much faster. The training cost is lower. So definitely something that we can experiment with, and different neural network libraries such as TensorFlow and PyTorch, they all have these already available for you that you can experiment with and use without having to code it yourself. And since this was just a brief introduction, I thought it might be useful to have some different ways you can learn more about it and dive deeper. So at Carleton, There's the Comp 4105 and 4107 courses. So 4105 is machine learning and 4107 is neural networks. In both of these, you go pretty in-depth into neural networks and definitely recommend those courses. There's also an online course, so Deep Learning Specialization by Andrew Ng. And this is a very popular and really good set of videos on Coursera, and they go into great detail and are very good, highly recommend. And just in general, there's tons of videos on YouTube that you can type in any topic that you're interested in, and you'll probably find something related there. And if you're interested in computer vision with neural networks, some of the examples I used were from the CS231N course at Stanford, and they have all their videos free on YouTube for the lectures, which is really good. So highly recommend you watch those if you're interested in computer vision with neural networks. And we also have the workshop for using image data and predicting that with convolutional neural networks coming up in a couple weeks or a month. So recommend you attend that as well. So that kind of concludes the lecture, or just the introduction portion in the background to neural networks. So right now, Victoria is going to do a code demo to see how it all works in action with code.
Hello, everyone. So, yeah, my name is Victoria. I'm a Master's of Applied Science student here at Carleton in computer engineering. And I'm just going to go over a code demo. I'm going to share my screen. Let's see. Didn't share the right screen. There we go. Can you guys see the notebook?
Yep.
Awesome. Cool. So I'm going to try and do this like on the go. I do have it copied in a filled out notebook. We'll see how this goes. But basically, I'm just going to do a quick introduction to how to build a simple neural network with CAIS. So as you've heard before, deep learning has kind of become this like big thing in machine learning that everyone wants to do. And it's kind of behind some innovations in very many like application areas. And here we just want to build the foundational concepts for deep learning so you can go on your own and do more complex things. But in this workshop, I'm going to use CAIS. And there are other modules and packages you can use to do machine learning, like PyTorch is one of them. But CAIS, I just picked CAIS because it seems like something that's pretty simple to grasp. So we're just going to load data, define a CAIS model, compile a CAIS model, fit, evaluate, and make predictions. And you'll see what all that means in a couple minutes. But here I use some resources. So first, we're going to need to load some relevant models. So CAIS is kind of an easy-to-use machine learning module under the package TensorFlow. And then we're going to use NumPy and Pandas just to help us out. So just some background on CAIS. So CAIS supports two model types, the sequential model and the functional model. And sequential model is just to say that your neural network is just a plain stack of layers on top of each other, where each layer has exactly one input tensor and exactly one output tensor. And that basically just looks like what you saw on the slides, where all the nodes in the previous layer connect to the next layer, and there's no like splitting or residual connections. So you don't use a sequential model when your layers have multiple inputs and outputs, or you need to do layer sharing, or you want nonlinear topology, so residual connections. And that's something that you'll discuss in another workshop that'll cover LSTMs or RNNs. So if you want to do something fancy like that, you would then use a functional model. So here's kind of an example of a sequential model, and I'll go further into what these mean in a couple minutes. But basically, it's just like a stack of layers, one on top of each other, nothing too fancy about it. So CAIS supports many layer types, like very many layer types. You have your core layers, which are just things that you typically use, and they're convolutional layers, which is for like computer vision and image processing, sometimes used for other things, but mostly for those. And then your pooling layers that are used for regularization and recurrent layers and normalization layers and so many other layers. And that was not the complete list. So there are so many layers, but we're just going to focus on 3 layers today: the input object, the dense layer, and the activation layer. And those are all you really need to kind of set up a simple neural network. So the input layer is just used to instantiate a CAIS tensor. And a CAIS tensor is like a symbol. It's basically like a vector. And so symbolic tensor like object, which we augment with attributes that allow us to build a model knowing inputs and outputs. So long story short, it just instantiates the input to the network. And that's basically the most we need to know about it. So that line of code to create the input kind of looks something like that. And we'll go into that in a second. So the dense layer is just a regular, densely connected, fully connected neural network layer. And again, all that means is that every node in the previous layer has a connection to every node in the current layer. So a dense layer, all it does is it takes the dot product of the weight matrix for that layer, multiplies it with the input to the layer, adds a bias, whether or not you're using biases or not, and then applies the activation function to the result. So the dense class has a couple parameters, but the most important ones are units, activation, and use bias. So units is basically just how many nodes or neurons you want in that layer. The activation function is whether or not you want, what activation function you want to use, whether that's sigmoid or softmax or ReLU or leaky ReLU. And if you don't specify anything, no activation is applied, which kind of means linear. And then use bias, whether or not you want to use a bias in that layer. So then there's the activation layer, which just applies an activation function to an output. This doesn't really have any weights or learnable parameters, but if you didn't specify activation in the layer previous, technically you could just have an activation layer right after that applies the activation function, and it essentially does the same thing. So a lot of these classes and methods allow for customization. So you could come up with your own activation function and input it in, and it'll use it. So there's a lot of customization you can do in CAIS. So let's actually get started. So our problem domain, since we're just going to build a basic CAIS neural network, we're only going to work with tabular data. And the data set we're working on contains 13 attributes that should help us predict whether or not an individual has heart disease. So some of these attributes include age, sex, chest pain type, resting blood pressure, and all these good features that might help us determine whether or not someone has heart disease. So I am going to read in our data set. And I'm going to use pandas because the dataset file has some weird characters in it that the numpy load txt function doesn't like and can't handle. So the pandas read CSV handles it pretty well, and then I'll just make it a numpy array afterwards. So then I'm going to shuffle the data set because the data is organized by class. So we don't want to train the network on like all positives and then give it all negatives to test. That'll just give us weird results that tell us nothing. So hopefully that works. Awesome. So we have 303 examples, and then our 14 columns are the 13 features, and then the target class. So 303 examples is actually really, really small for deep learning, like really, really, really small. You want like thousands and tens of thousands of examples to truly train a neural network. But in our case, we're kind of just learning and experimenting here. And we're going to build a really, really simple neural network with like 2 layers and very few nodes in each layer. So for our case, it's okay. But in general, it's not something you kind of want to do. So then we're going to use 75% of the data for train and test. I'm just going to copy the code in here. And so our training set will have 227 examples, and our test set will have 76 examples. So there are multiple ways to define the model in CAIS, and you'll end up with the same result with any of these ways. So we'll proceed with a similar fashion to example in the CAIS documentation tutorial, just to keep things the same. So the first thing you want to do is create your input layer, like we talked before. So we're going to have our input layer, and that's basically just going to be our input constructor. And we're going to say the shape is 13 because we have 13 attributes. And then I'm just going to call it features. And that will be our input. And then what we're going to do next is add a fully connected layer, or dense layer, as it's called with CAIS. And we're going to say how many units in that layer, and we'll use 8. We're going to have our activation function be a ReLU, which is really popular nowadays. It has something to do with the speed of training, but we're not going to go into the math right now. But typically people like using ReLU, at least for the hidden layers. And then right here, we're just going to it kind of looks like a multiplication with the input. And all that does is that now your first layer is the input, and then right after that, the input layer feeds into the dense layer. And that's all that this bracket kind of looks like, with the multiplication with the dense layer. So I'm going to do that again. We're going to have 2 layers. So we'll have the next dense layer, and then I forgot an S right there. And that one's going to have 4 units. The activation function will be ReLU, and then we're going to multiply it with these brackets here from the previous layer. And then finally, we have an output layer. And that's just going to have 1 unit because our problem is binary classification. So we only need 1 unit because you can have the 0 or 1 with that 1 unit, and that'll tell you which class. Then our activation function will be sigmoid, and we choose sigmoid for this last activation function because it transforms the value somewhere between 0 and 1, and we can kind of call that a probability. If you had like multi-class classification, you would use a softmax function, which is just an extension of a sigmoid that can be applied to more than 1 output. So then we will define our model as a CAIS model, where our inputs are the input that we created, and then the outputs are the outputs we created, and then we can print out a model summary. Hopefully that works. I think I've got an S there. There we go. So here you can print out a model summary, and then we'll have it'll just give you the summary of all the different layers, our input layer, our 2 hidden layers, and then our final layer here, how many parameters they have in each layer. And it'll also tell you the total number of parameters, which is 153, and the total number of trainable and non-trainable parameters. And the difference is that for here, we just use simple densely connected layers. And all the weights in those layers are trainable. So when we update during training, the weights get updated. We have no non-trainable parameters. So that means there's no parameters that will stay the exact same no matter what we do during training. So next, we have to compile the model. So when we compile the model, the backend uses a bunch of numerical libraries that'll transform a model into a representation that allows the computer, either CPU or GPU, depending on what you're using, to train. And to compile, we specify some additional properties that are required to train our network. So we have to specify the loss function that we use to evaluate our model. We have to specify the optimizer, which is what actually determines how we update the weights. And then we can specify any other metrics we would like to keep track of during training. So in this case, we're going to use binary cross entropy for our loss function. And that's just a very, very common loss function used for categorical problems, specifically binary categorical problems. And then we're going to use the atom optimizer, which basically just applies stochastic gradient descent with some modifications that make it better. And then we're going to collect and report classification accuracy, just because this is a classification problem and that's a good metric to keep track of. So essentially, we're just specifying some training configurations, and the backend will take care of the rest. So there are so many optimizers available, and all of them really apply like gradient descent, but they take some liberties or they apply some modifications to make it better in some way. So then loss functions and metrics need to be chosen carefully based on your problem, right? So if it's a classification problem or a regression problem, you would choose different loss functions. If it's if there's a large class imbalance, you would choose a different metric, right? Because some metrics don't really tell you, are not really susceptible to class imbalance. They'll kind of lie to you about the goodness of your model if there's a large class imbalance. So you kind of need to pick your metrics carefully. So there are a whole bunch of loss functions available. You know, binary cross entropy is a good one for classification. Then, you know, for regression, we have mean squared error, mean absolute error, and so on and so forth. And then metrics, we have accuracy, we have mean squared error for regression metrics, and we have precision, recall, and area under the curve for classification metrics based on true, false, positives. And here's where you need to keep an eye on whether you have class imbalance, because something like precision will tell you a lot more about a class imbalance problem compared to area under the receiver operating characteristic. So we can actually write the compile code now. And all that is calling this compile method and specifying our optimizer to the one you want to use, the loss, and the metrics you want to keep track of. So here I specified the learning rate. So the learning rate is just a number that gets multiplied by the update to the weights. And it kind of tells you how big of a jump you want to make when you're training. So if you make too big of a jump, then your model will just jump all over the place and not learn anything. If you take too small of a jump, then your model won't learn anything at all. So the learning rate is also something that you can find out by experimentation, hyperparameter tuning, whether that's grid search or random search, to try and figure out which one is best for your problem. You can also use hyperparameter tuning to figure out whether you want to use atom or regular stochastic gradient descent as well to figure out what's best for your problem. So we have compiled the model. So now we actually want to fit our CAIS model. So we can use this fit function, and training occurs over epochs, and each epoch is split into batches. So an epoch, as was mentioned before, is one pass through all the rows in our training data set. And then a batch is one or more samples considered by the model within the epoch before the weights are updated. So based on the version of gradient descent you're using, you might look at one example, then update your weights, then the next example and update your weights, and then go through the entire data set. Or you could look at 10 examples and then update your weights, or 100 examples and update your weights. And the amount of examples you look at before updating your weights is a batch. And when you make it through the entire data set, that's an epoch. So here we're going to call the fit method, give it the training data, the train classes. We're going to use a batch size of 25, and we're going to train for 500 epochs. And that's going to take a little bit. And here we can see as it's learning, the accuracy on the training set is improving, and the accuracy on the validation set is kind of improving. And then our validation loss and our training loss are decreasing, and that's good. So let's see. And here we go. So now that that's done, if we go back to look at what the code that I wrote, I set the model fit to this history variable, and all that kept track of is our losses, accuracies, and validation loss and validation accuracy over training. So what we can do is we can look at the history, and we can get this, if I create a data frame, we can get this nice table of the values over each of the epochs. And we can also plot it just to see what happened. So first, I'll plot the loss. And as we can see, the loss decreased over time, which is kind of what we want. And then here, if we plot the, is that the validation loss again? Oops, let me see, let me get the accuracy. There we go. And here's the accuracy over time. So it learned a lot in the beginning here, and the accuracy improved greatly. And it's typical for the accuracy on the validation set to lag behind the training set, because the training set is what it's actually learning on, and the validation set is just something you're using to determine performance. So here I actually used our test set as our validation set, and generally good practice is to have a training set, a validation set, and a test set. So your final test set is something that the model has never seen and you've never used for hyperparameter tuning, for example. So that's kind of what happens during training. So we can evaluate the CAIS model and make predictions. So we evaluate the model by on the test data by using our evaluate function, and all that is passing through our test data set, and then we give it X test, Y test, we just give it a batch size, and then we can print our results. And here we can see that we get the loss on our test set, and then we get the accuracy. So we get a 67% accuracy. So when you call evaluate, it gives you an array of two, or a list of two values. Again, the first will be the loss, and I'll use whatever loss type of loss you specified when you compiled. And here will be, and the rest will be the metric, whatever you specified when you compiled the function, or compiled the model, sorry. So evaluate just returns the loss and the metric. It does not return the actual predictions for the data. So to do that, we can call the predict. The predict method here. So if we predict on the first three rows of our test data, we can print out these predictions, and then we can print out the true values to see how it did. Here we go. So here, so on these three predictions, it got two of them correct and one of them wrong. So when you, since the output of the model the last layer, remember, used a sigmoid function, and that just changes the values from 0 to 1, which then we can use as a prediction confidence. So you could take that output and round it such that values below 0.5 become 0 and values above 0.5 become 1. And now you kind of have a binary classification. So rounding it just enforces a 0.5 confidence threshold. Anything above 0.5 is a positive class, or whatever you determine the positive class to be. And in our case, it's whether the person has heart disease. And 0 will be the person does not have heart disease. But not all models will work the best at this 0.5 threshold. So you could use a different threshold, which means you can like programmatically define what is a positive case, at what confidence is a positive case, and what confidence is a negative case. So here, if we use that 0.5 threshold, all our 3 examples in our test set, the first 3 examples, are below 0.5, meaning that if we apply the confidence threshold of 0.5, all of them would be 0. But our true values are 0, 1, and 0. So kind of for this middle one, no matter what confidence you picked, it'll kind of not do well. So there are ways to pick your confidence threshold by looking at a PR curve or a receiving operating characteristic curve and finding the threshold that maximizes your recall or your precision or your false positive rate. But here we're kind of just playing around. So 0.5 might work out if we were to do that. So that's all I have for our introduction. Next week will be an interactive workshop where you'll build your very own neural network. So be sure to be ready to follow along and participate. And make sure to follow us on Facebook, Instagram, and our website. If anyone has any questions about the content, now would be a time to ask either of us. Yeah, for next week, I think Google Colab should be sufficient. No problem. Yeah, there's so much like machine learning or AI stuff around. There's always new papers and new concepts. And like even now, a couple of years ago, LSTMs were like the best thing ever. But now if you use LSTMs, you're behind. You need to use transformers or something. So like machine learning is a big, it's rapidly moving. It's a rapidly moving research area. Yeah, so the recording of this workshop will be available on YouTube sometime in the next couple of days, but it should be available. We'll also post a link to the notebook that I was working on. It'll be uploaded to Kaggle, and there'll be a link on the website. If no one has any other questions, thank you guys for coming out. We hope to see you next week for our first project workshop. Yeah.